Hello and welcome to Refactoring, Safe and Effective. Before we get started, I want to introduce myself. My name is Max Guernsey III. I'm a second-generation programmer. I have almost 30 years of experience. I've used numerous languages, tech stacks, platforms, whatever. I'm an expert in test-driven development, design patterns, refactoring, behavior-driven development, requirements analysis, and more. In this video, I'm going to talk about a number of things. First, I'm going to talk about why changing code is hard or why it gets difficult over time. Then I'll explain the theory behind or which underlies refactoring. I'm going to give a live demo. I'm going to show you how real refactoring works using Visual Studio, ReSharper, and some sample code. Let's start with changing code. This should be a fairly familiar process. We start with fast delivery. That's how a product usually starts. We have greenfield code, we start writing code, and it goes fast, it feels good. So this is great. Over time, things slow down a little, but the pace is still sustainable. We tell ourselves things like, well, I like for coding to be a little bit hard. I like a little challenge. I just don't want it to get too difficult. And then things slow down more. We say, well, it's getting a little hard to maintain, but we've sunk so much into this, we don't want to rebuild it. After a little while, it starts to take too long to make changes. And we tell ourselves, we got to stay the course, but man, I'm just under constant pressure to deliver more. And as we slow down, the pressure to deliver more increases. And that makes things worse. That makes us slow down more because we cut corners and things keep getting worse and worse and worse. And eventually, someone with some influence and some chutzpah comes in and says, we just can't keep doing it. We can't keep living like this. We need to take the code and we need to rewrite it. We need to build something new that we can maintain. And so then the project starts again, and we have fast delivery, and the cycle just continues and continues. I've actually been there at the tail end of a rewrite where things had gotten so bad during the rewrite that the company who initially commissioned the rewrite and spent $1 billion on it decided to cancel it and start again because of maintainability. So the question is, why does it get harder? We need to figure out why it gets harder. And to do that, we're going to need to do a little bit of analysis on what the drivers for decay are. Clearly, code bases are decaying over time. That's the word we use to describe it getting harder to maintain them. But what are the actual causes? Well, over time, code looks more and more like this. We don't know how it works, right? We look at the code and we can't just say, this is how this code works. We have to spend mental energy digesting it and processing it and really understanding it. Or we don't know how it should work. We can tell what the code does, or maybe we can't, but whether we can or we can't tell what it should be doing. Or it's just plain hard to read, or it's messy, it's convoluted, it's difficult to track down what you need. Perhaps there's some coupling. Perhaps there's some coupling. Of course there's coupling, but perhaps there's prolific and deleterious coupling that makes it hard for you to maintain. It kind of holds everything in place. Or in the other direction, maybe there's big classes. In the worst code bases, there's a lot of both, right? But there's big classes. The classes are too big. It's too hard to figure out what it's doing. It's doing too much. And those things are all coupled together too, but they're coupled silently because they're within a class. The same is true of big methods. I've seen some long methods in my day. I've seen methods 30,000 lines long. One method, 30,000 lines long. And of course, the one that everyone focuses on is there's not enough tests. When I make a change, I can't be confident that that change is actually going to create the effect that I need because I don't have tests to tell me. Let's break these down a little bit. Let's start with the first driver. I don't know how it works. Why would that be? That's because there's no information on how the code works. Why would that be? Well, it seems to me like a great place for that information to live would be the code. And so if somebody can't read the code and get the information they need on how it works, that means the code is itself unreadable. And that in turn means the design doesn't explain what the code does. The same is actually true of you can't tell why it works, right? You don't know how it should work. You don't have any information on how it should work. That's because the source code doesn't explain the requirements. And that's because the design doesn't reflect the requirements. Messy code is the same way. It gets messy because of inattention to design. Coupling gets prolific because proper boundaries weren't really set up. Big classes occur because the property boundaries weren't set up also. Big methods, same thing. And not being enough tests. If nobody ever sets out to have untested code. I mean, I know that in the old days, there was like people who wrote tests and people who wrote code, but in modern times, this is not how we're writing code bases. What's really happening when there aren't tests, there's a reason. And the reason usually is that the code itself is hard to test. When somebody says, I don't have time to write tests, what they mean is it takes a long time to write tests. And the reason for that is it's hard to write tests for this code. So that usually comes from things like you can't test parts, you have to test the whole thing, you have to mix together a bunch of behaviors, you need extra external hard to control resources, some sort of coupling or other design related problem with the code is standing in the way of testing it. So what you notice with all of these causes is that underneath the hood, it's design. It's always design. It's design that doesn't explain the behavior. It's design that doesn't reflect the requirements. It's design that doesn't create the proper barriers or boundaries. And it's design that doesn't support testing. It's design. Design is what decays over time. And design is what makes it hard for us to write new features and to update existing code. All software work is design work, so it shouldn't be a surprise that decaying design is a problem. People don't make software. People make plans to make software, and then machines take those plans and turn them into software. You're always updating a design. And so since you're always updating a design, it, again, shouldn't be a surprise that as design gets worse, it causes you to go more and more slowly and have to move ever increasingly carefully. And of course, it should be no surprise that it's what makes testability hard. But the real question is not, is design the problem? I think that that's pretty much, if not self-evident, it's pretty obvious in retrospect after having done the analysis. The thing that we really need to understand is, why do designs become so hard to test and change over time? Now, nobody is setting out to make a bad design. That's not a thing that happened. I mean, there was one example in my career, 30 years, I met one guy who was trying to make the design worse so that only he could maintain it. So effectively, people aren't doing that. What's really happening is people are starting out with the best design they can imagine, given the requirements that they need to implement. Then, at some point, because the universe isn't perfectly predictable, we meet a requirement that nobody thought of, and that requirement violates some assumption in the initial design. Now, at that point, we have a choice. We can either change the design to incorporate that new, or to reconcile with that new understanding, that new requirement, or we can continue to work within the design. When we make the decision to work within the existing design instead of changing it, that's when we find that we cause decay. That is what causes the design to change in a bad way, but a transparent or invisible way. We refuse to change the design, or we think we refuse to change the design, but we're always changing the design because it's all design. And instead of creating a new class or a new interface or a new something, we create invisible coupling or invisible redundancy or some other design structure that makes the code worse. It is failure to modify design that leads to the decay and the descent into unmaintainability. And then we say, well, if that's true, I think that that's pretty clearly true. But the way I presented it, it almost seems like a foregone conclusion that then we should always change design. So why don't people do it? That too is not malice. There's a reason. There's two forces that push back. One is people say, well, we don't have enough time. I'm under this immense pressure to deliver. There seems to be an insatiable demand by the business side of the organization for more. I'm under these tight deadlines. I'm up against a wall. I've got to get it done. And so I say, I'll come back and fix it later. Now, I don't actually think that argument holds up in real life, because if you don't have time to fix the design now, you definitely don't have time to fix the design later, because you'll have an accumulation of additional design problems that slow you down. It's going to take longer to fix later than it will now. So that argument, I don't really want to address. I think we'll find that it ties to another argument that I want to look at, which is it's dangerous. You have these critical areas of the system. This is where this always breeds in my experience. You have these critical areas of the system. They're parts of the system that are important. There's a very high risk associated with breaking them. And because of that risk, when someone gets to the change it or leave it as is and try to work within the design, try to kludge stuff into the existing design decision, they choose the make things worse later but not have them break now path most of the time. It's the danger that I think really matters. Now, there's a third option. There's a third cause: public APIs, public SDKs, those kinds of things. It's kind of a special case. There's solutions that exist for it, and they still require an investment in design. They're kind of out of scope because there's like a marketing aspect to that almost, or a product management aspect that I don't want to get into in this webinar. For this webinar, I really want to focus on the danger. People don't change designs, or they don't change the critical parts of their design because it's perceived as dangerous. So we have two forces that are now in contention. If we don't change our design, it's going to get worse. Or if we try not to change our design, it's going to get worse. We're always changing design, right? But then when we explicitly change design, it's this scary, risky thing. Now, nobody has ever figured out how to eliminate change. Not ever. That's, waterfall is an attempt to imagine that you could have a project that has a beginning, a middle, and an end, and nothing's going to change in between. And we saw how poorly it worked out. You cannot make change go away. But people for thousands of years have been mitigating dangers and eliminating dangers altogether. And in this case, that's what refactoring for. Refactor is like our equivalent of like a campfire and a spear, right? It's going to protect us. True refactoring is going to protect us while we're making our design changes so that we can keep our code healthy and clean and have it not get harder and harder to work with. Let's dig into the actual theory of refactoring itself, real refactoring, not just changing design. So I'm going to show an example, and then I'm going to show a demonstration in a minute. But first, I want to establish some kind of like framing things. I want you to understand why we want to refactor. I want you to understand what refactoring is in its essence, and I want you to understand the kind of core refactoring loop. Once we've done that, I'll give you an example of a refactoring operation, and then we'll switch over to Visual Studio, and I'll give you the demo. So we'll start with what refactoring is. Refactoring is changing design without impacting its external behavior. It is a methodology. It is a discipline. It is an approach. It is not a set of tools. Remember, originally, it was a manual thing. We figured out how to refactor first, and then people started building tools out of those processes that allowed people to do that a little faster and a little bit more repeatably. It's the method that matters, the method that is the key. Now, why do we refactor? Why is it important to refactor? Well, the primary risk that holds people back from changing designs is negative impacts on behavior. We don't want to change a design that's a critical design that's in the center of the system because we're afraid we'll break everything. And maybe it's a legacy system where we don't even have tests to tell if we will, or maybe changing the design will require us to change the tests. And so we can't really trust the test to tell us that that was a good design. Refactoring is a way of guaranteeing, almost guaranteeing, no impact on behavior. It dramatically reduces the risk to changing design. And by effectively eliminating that risk, it tips the scales. So before we had this balance where maybe we were choosing between changing things and taking the risk now, and some of the times we're choosing decay later because the risk now just seems like too much. But when we add refactoring, it squashes that risk and tips the scales. We can always change design now. Okay, let's look at the methodology here. Let's start with an example. The classic example is extract method, or now people call it extract function. The procedure is very simple. We start by validating a set of preconditions. Do we know what code we're going to extract? If you're using automation, that's selecting the code. Does it have a return value? And if so, have we identified it as a variable outside the code block? Is it updated inside the code block? Are the parameters also defined? And are they defined outside the code block? And then we go through 5 steps. We define a new method. That's not going to change behavior. Finding a new method, and especially like a new private method, can't change behavior because nothing's calling it. We copy the return variable definition into that method and return. Again, that method isn't being called. So it doesn't matter what changes you make, but also you're taking code that already does something and copying it in. So it's like 2 angles of making sure you're not changing anything. Then we copy the variable definitions. We take all of the variables that impact the code we want to extract, and we paste them as parameters into that new method. The method isn't called, so again, it's safe. And then we copy the block of code out of where it was and into the new method, because it has all of those variables it needs as parameters, and because it has the return value as a variable, and because it's returning the value at the end, it's preserving the behavior of that block of code. Plus, we're not calling it yet. That's what leads us to the last step, which is to replace the block of code with a call to the method. Each of these steps guarantees that the system will work the same way after as it did before, and therefore all 5 of them together guarantee that the system works the same way at the end as it did at the beginning. This is kind of the essence of refactoring, is moving in these small, provably transformative steps. Let's see how that looks concretely. So we start with some code. Here we have some code that takes a list of votes and computes a number between -1 and +1 by dividing the yays, the count of yays, minus the nays, by the total number of votes that didn't abstain. So it has to subtract the abstention from the denominator. Now, an important thing to understand about refactoring is we don't actually care how this code works. We only care that it works the same way after our extraction as it did before, because refactoring is about preserving behavior and changing design, and therefore only changing design. So let's go through the process. We'll start by checking our preconditions. Do we know what code we want to extract? Yes, we're going to extract the thing that counts the number of non-voting votes. Do we have the return value defined? Yes, we do. We have that in a variable and it's initialized. Is it assigned? Yes, it's updated here in this for loop. Are the parameters defined as variables? Well, in this case, the parameters are other parameters of the containing method, which amount to the same thing. So let's proceed. We create a new method. We're going to call it count non-voting, and it returns 0. Doesn't really matter what it returns. It could throw an exception because it's not being called. It doesn't do anything yet. And then we copy the return variable definition into it and make sure we return that. Once we have that in place, we copy the variables, the list of votes, and paste them as parameters here. And then we copy the code we want to extract and we paste it into the method in between the definition of the return variable and the return of the return variable. Now we have a complete extraction of that code. The only thing left to do is to replace that original block of code with a call to the method. Let's take a look at what that actually did. So when I checked the preconditions, could that have impacted compilation or behavior? No. When I defined the new method, could that have impacted compilation or behavior? No. I mean, I suppose while I was typing it, the system wasn't in a compilable state, but it was very short. And at the end, when it did compile, it did the same thing as before. And this is actually true of all of these steps. So the whole way through this process, we're preserving the behavior and we're creating a very kind of strict, rigorous procedure that leaves very little room for interpretation and doesn't really create a lot of space to make a mistake. And this is the pattern. Every operation strives for transformation. No impact on behavior is to be allowed. That is your your first principle is no impact on behavior. Ideally, before and after each step, it compiles. But if it doesn't, at least make sure that from compile point to compile point, compilable point to compilable point, there is no impact on behavior. Each operation is easy to abort. The individual steps you can just undo. If you've got an entire transformation, you can go back to the last commit or even dump a branch and start over. If you keep everything small and controlled, it's easy to say, oh, this didn't work, let me try again. The focus here is on safety. We have sequences of steps, and each step, because we know that step is transformative, we also know it's safe. If we make a mistake, we choose going back to the last known state where things were good and trying again, rather than just powering through. This gives us very limited risk with easy remediation when we do make a mistake. And this pattern applies to all refactoring operations, whether it's introducing a variable within a method or transforming a constructor into a builder pattern. Now I want to drill into this abort and retry strategy a little bit. I've seen lots and lots of cases where just trying to power through once you make a mistake creates a huge mess and makes things take a lot longer. Basically what's happening is people fall into the sunk costs fallacy, and then they start doing things to try to get back on track and preserve all of the work they've already done. And so they start taking steps that aren't safe, and that is what creates the mess and makes it take long. But aborting the current operation is non-destructive. When you go back to the last known point, you're at a known point, right? You know it worked a certain way before you started refactoring. If you just cancel that refactor and go back, at least there's no harm. You might not have made progress, but there's no harm. And it gives you a chance to move forward. It also gives you an opportunity to try a different path. If you just flubbed it, you could just probably use Control-Z and go back a step and try that step again. But if you realized, I actually was headed down the wrong path, I don't need a strategy here, I need a visitor or whatever, then you can take the knowledge you gained from the previous iteration and try again on a new path. So the number one principle is you focus on small, verifiably safe, transformative steps that you can prove with math did not change behavior. The next principle is the goal. What you know is safe, what you know is transformative. It's things that only change design. So when you make a change, it must change design and only design. If it modifies behavior, it is not refactoring. If it might modify behavior, it is not refactoring. And the third principle is don't push forward when things don't work out. Instead, step back to the last point where you know things are safe and try again. One thing that people really have a hard time with is when they see a bug while they're refactoring. They'll be refactoring, they'll be fixing things, and all of a sudden the design becomes clear enough that instead of being hard to tell what the system does, it's easy to tell what the system does. Or instead of being hard to tell what it should do, it's easy to tell what it should do. And then they can see a bug. They can look at the code and they can read it and they can understand it. And they say, it shouldn't do that. That's going to be a big problem if that ever happens. And they want to fix it. Don't. I'm not saying don't fix bugs, but I'm saying don't fix them while refactoring. Fixing bugs is changing behavior. Refactoring is changing design and only design. And that means that even the bugs must persist. Okay, let's get into our demonstration. I need to give you just a little bit of context so you understand what it is. that we're working with. The domain here is tax accounting. I know that's boring for most people, but it is also something that almost everyone understands. We're going to have a class called Transfer Manager. It handles transfers between accounts. It makes sure that those transfers are compliant with different sets of tax rules. It makes sure that there's reporting, and it makes sure that there's any validation that occurs. Currently, it uses a switch on an enum value to make that happen. So it's something like this. We have the transfer manager. It uses a transaction in one way. It uses an account, uses a governing body, and it uses a tax rules enum. And it uses a switch statement to make a decision about how to coordinate between all of these things, especially the tax rules and the governing body. Then you might say, what's wrong with switch statements? Nothing is wrong with switch statements themselves, but they do have a tendency to proliferate when you use them like this. So if you imagine a situation that's more realistic, instead of just one little part of a system that handles one little rule, you have 9 switches and 9 different cases that they each have to deal with, but they're all driven off of the same enumeration value. And now you need to add a case or remove a case, or maybe update some combination somewhere. The risk that you're not going to find everything that needs to change is very high. It's very high. The more complexity you add this way, the higher it gets. So switching on an enum is okay, but what we really want is for there only to be one switch, and when we use object-oriented programming to manage everything from that point on. And in this case, what we're going to do is we're going to replace our switch with a strategy pattern. We're going to replace it so that instead of having a switch inside the method that it has the polymorphic behavior, we're going to inject a method that handles the tax rules itself. The result of this is going to be that the transfer manager is open-closed. That means that we can add new tax rules without ever touching transfer manager. It's going to become blind to each individual tax rule. So the target design is going to look something like this. We have our tax implications, and instead of it being an enum, instead of a tax rules enum, we have a tax implications object. And we have one for each case, and it's going to handle the tax rule specific logic. And transaction manager is just going to unconditionally call it. Now let's look at the actual code. So here we have the transfer manager. And it has one method called transfer. It takes a account, a source account, and a destination account, an amount to transfer, and a set of tax rules. It then creates a transaction unconditionally, performs a verification that always must be performed, which is that you need to make sure that you have enough money in the source account to transfer to the target account. And then it throws an exception if that's not the case, which is caught down below. And then we have all of the tax rule specific stuff. We do one thing if it's tax deferred, a contribution, another if it's tax deferred withdrawal, another if it's a Roth contribution, and another if it's the repayment of some expense, like a reimbursement for an expense. So we do these 4 different things. And in real life, of course, it would be much more complicated, but this is good enough. And then we just kind of ignore this transaction aborted exception because it's just used to control flow within this one method. Okay. So what do we want to do? We really want to get this switch statement out. And the first step to that is going to be to make a new method. And we'll call it apply, because we know this is going to live on a class called tax implications, and tax implications.apply seems to make a lot of sense. And we're going to need all of these parameters, so we'll just accept that. That creates the method we need. Now, part of the strategy pattern is that the method with the variation lives on another object. And we don't have that. We don't have the individual concrete objects, let alone the abstraction. So let's use transform parameters to create that. Now, the thing that I really want to be part of the object is the tax rules enum itself. That's what I'm encapsulating. Everything else is different from transaction to transaction. This is the same for any given instance of a particular kind of tax rule. So I will unselect all of the parameters that I'm not going to have be part of my tax implications object, and then make a tax implications class. Then I'll inline some stuff that doesn't make sense to have. It's just ReSharper adds that because it makes it easier for it. Okay, so now I've got a method, and it takes tax implications and these other parameters, and I want that method to be a part of tax implications. So I'm going to use make method non-static to move it. And when you do that, you have to choose a parameter to move it to. And I choose the tax implications. And now you can see I have a tax implications object that's created, and I call apply. This is the shape of the method that I want. I want this method, I want this transfer method to have a tax implications object that it calls apply on. But I don't want the tax implications object to be created internally. I want to pass it in. So I will introduce it as a parameter. When I introduce it as a parameter, I no longer need this tax rules parameter. So now I've got something a lot more like what I want. But I don't have the strategy pattern yet. I don't have the abstraction part of it. This method looks exactly how I want it to look. Next step is to create the abstraction. The first thing we'll do is make sure that nothing is coupled to this constructor, because coupling to a constructor is coupling to the concrete identity of a class, and what we need is coupling to the interface of the class. So I will use replace constructor with factoring method to do that, and get instances as good a name as any. The next thing I'm going to do is add a switch statement, and I'll switch on the incoming tax rules, and I can add a branch for each of these rules. So I'll add a branch. You might say, well, that's not behavior preserving because it throws this exception, but it never is actually going to reach this branch, not with the current state of the code. This would only get invoked if somebody added a new tax rule. So we don't have to worry about that. Now what I'm going to do is I'm just going to copy this line. This doesn't change behavior. Now we return, we return, we return, we return, we return, and we return. Get rid of all these breaks. And that allows us to get rid of this return down here. The result is the exact same. We're just using this same return that we were always using. Now I can start creating the classes that I need. So I'll create one for the no tax implications. That's safe to do, right? And I'll need a tax rules. Tax rules. That's safe to do. And then I can say tax applications rules. That hasn't changed anything. Now I can create a new instance of this instead of just base tax applications. And I can repeat this process as needed. And we'll just repeat and repeat, repeat. And what I'm doing is I'm just duplicating these guys and pasting in the new names. And then I copy the name and I use it in the new statement. 2 more to go. One more. Now we've created a class hierarchy invisibly. From the rest of the code's perspective, this hierarchy doesn't exist, but we know it exists, and it exists for our purposes. But it hasn't changed behavior because every no tax applications is also just a tax application. So calls to its methods are just going to be calls to the tax implications methods. When we create a no tax implication instance, we always create it when the tax rules is no tax implications. So we can copy that and paste it. And in fact, since we know we're always pasting it into the constructor, we actually don't even need this constructor parameter. We can paste it directly in. We'll delete this. And we can repeat this process as well. Paste it in here. And then we paste it in here. And we no longer need this. And we can just continue. And I know it may feel tedious, but it's worth it to have no changes in behavior and to be guaranteed you have no changes in behavior. And why was this important? This was important because it gets rid of these constructor parameters. We're still doing the same thing we've always done, but now we've tied this value to the type. Every instance of no tax applications always has a tax rule of no tax implications. That's actually critical to do. Okay, I'm going to make this method or this property virtual. And now I have an opportunity to override it. So I can, let's see, I can override it. And it returns base.tax rules. But what's base.tax rules? It's always going to be this. And I can repeat this process. That's the key here. Gradually moving things where they belong. So now, we'll override the tax rules. And we can say, what is this? This is always going to be what's passed in by the constructor. So I can just hard code it. Repeat. Override. Copy. Paste. Repeat. Override. Copy. Paste. Do that. Copy this time first. Override, tax rules, paste. One more. Tax rules, copy the expense payment, and paste. Why was that important to do? It was important to do because it means that we no longer need a concrete definition of this tax rules. First of all, we don't care what it's set to. And second of all, we don't need it to be virtual. We can have it be abstract. Of course, that's going to require us to make it class abstract. But that's okay. That hasn't changed the value at all. And that allows us to remove this constructor. So now we have a polymorphic hierarchy. It's barely polymorphic, but the polymorphism does exist. We have a bunch of different types, no tax applications, tax deferred, and each of them specifies the tax rules. We'll see why that's so important in the next step. So the next thing to do is to take this method that we wanted to be a strategy method, that we want to transform into a strategy method, and to use push down. We're going to push it down to all of these classes we just created, and we're going to make sure that we leave an abstract interface for it in the base class. This is going to create a copy of this method in each of the child classes. This allows us to get rid of this abstract tax rules method because there's no coupling to it anymore. All of the coupling to the tax rules overrides are actually coupling to the implementations directly. So we'll delete this and we'll make sure that we only delete that member without its inheritors. Now we can get rid of the virtual tag. And once we do, we can inline tax rules. Having done that, it becomes abundantly clear which branches actually matter. You can get rid of all of this unreachable code. And we don't need the switch statement because it does nothing. We can play the same game with each implementation. We can inline the tax rules, and we see that one branch is called and the others are not. So if we convert it to an if statement, we can then replace the if statement with just the branch that actually gets called. And so now we have the logic for the tax-deferred contribution implications in the tax-deferred contribution implications class. Let's keep going. Make it non-virtual, inline it, and that allows us to choose just the branch that matters. Again, we repeat. Inline. And we see there's one branch that matters. We'll move it to the top. We'll convert this to convert this. See, I just aborted and retried that step. Convert it to an if statement and choose the one branch that matters. Repeat again. Inline. Find the branch that matters. There aren't any, so we can get rid of the unreachable code, and then we don't need the switch statement. Last one, I think. Inline. Move this to the top to make the refactor a little easier. Make it into an if statement. Choose just the branch. All right. So there's not much left to do. We've definitely externalized everything. We could move this class to another file. Now we've done that. But we've made tax applications into an abstract class. Transfer Manager now takes a tax applications instance and simply applies it. I think it's easier to read now. We get a transfer. We've got a source account and a destination account and an amount to transfer, along with some tax applications. We create a transaction, but we don't commit it. We verify that we actually have the money to transfer and abort if we don't. We apply the tax rules, the tax implications, and then if all of that succeeds, we commit the transaction. This is a very straightforward, high-level, well-abstracted, or at least better abstracted version of the transfer behavior than we had before. This applies to all situations. It's not just operations that are automated. It's not just one or two automations. This is a way of thinking. This is an approach. It applies to all code all the time. The only thing that really varies is speed. If you understand the code better, you can go faster. If the code is better, you can go faster. If you have better tooling, you can go faster. Like I can go really fast on code like that when I'm not explaining it. I can't go as fast on Blazor code because the tooling isn't as good. But I can still do it. The more practice you have, the faster you're going to go. But it always works, and it always works the same way if you're disciplined about it. It's something you can learn. I've helped hundreds of people do it already. It's a matter of attitude and priorities. That's the most important thing. Adopt the attitude that you're not going to change behavior when you're refactoring. Just decide you're not going to do it. Prioritize it. Make sure that you are taking a design-first approach to your code, and then that when you need to change design and you don't have tests to fall back on, you can make sure that you find ways to change it that don't change how it behaves. It stops being something you do some of the time and starts becoming the way you approach code. It takes time and investment to get there, but it is more than worth it. Now, I didn't run any tests there. I have the tests. I could switch over and run them now. I'm not gonna. In live ones, I usually do. But I don't run them just to prove a point. I didn't do any steps that were unsafe. I can prove those steps were safe. I don't need the tests to prove they're safe. Now, I'm not saying you should actually do that. If you have tests, use them. You should have tests. You should be using test-driven development to make sure you have tests. It's a great way to do it. But you're going to run into code that doesn't have tests. Your tests don't have tests, right? You're going to need to change the design of code without tests some of the time. Legacy code, there's tests, there's code that adapts in stuff that's kind of from outside your system that's hard to test or that shouldn't be tested by you, that should be tested by a third party or something like that. You're going to need to change those things. And when you do, the approach you should use is a disciplined refactoring approach. Sometimes design is going to get in your way. That's when you refactor. Focus on small, verifiably safe changes. Only change the design, never behavior. Now, this isn't saying like throughout your entire career. That doesn't make sense, right? But when you're refactoring, when you call what you're doing refactoring, be 100% certain that you are only changing design and not changing behavior. If you have any uncertainty, abort, try again. If you keep your steps small, the cost of that is really, really low. And the cost of committing to a path that might be bad can be huge. Sometimes you have to make things a little worse in order to make them better. I kind of reversed the saying here on the slides. I do that partially because I think it's funny, but partially to make a point. We can't unscramble an egg. We haven't figured out how to do that. I don't know that we'll ever figure out how to do that, but you can unscramble code. Sometimes you have to make things a little worse in the short run. For instance, I pushed that method down and immediately created 6 copies of the same method. If someone had a real clean code perspective, they'd go, wow, you just made it worse. You just created 5 redundancies. Why would you do that? The reason I did that was so that I could safely transform to having less redundancy. I got that switch statement concentrated into something that created a tax implication object. If I had another switch statement somewhere else around tax rules, I could merge it using another path and have one switch statement for both of those things that creates one kind of tax object, each implementation of which knows all of the rules for that set of tax implications. So sometimes you have to make things a little worse in order to make them better. Be sure you're doing it the right way, though. The results are worth it when you do. Now, a risk here is you can refactor to the wrong design. You could refactor to a worse design. But that's not a risk inherent in refactoring. That's a risk inherent in trying to make big design changes. The mitigation, though, is that if you're good at refactoring, it's easy to be wrong. You could say, oh, I was wrong. Okay, I know how to get back from where I am to where I was before. Obviously, there's the abort and retry option, but let's say you make the wrong decision and 3 weeks later, after a bunch of behavioral changes, you realize it was wrong. Refactoring gives you the tools you need to adapt. And so it's okay to refactor back. All right, well, thank you very much for giving me the time and watching this video. I hope you appreciated it. I hope I've given you something that's valuable. I'm Max Guernsey with Producore. Thank you. If you want to learn more, check out the full Refactoring 1 course using the link in the comments.